Good day to the Rafida. My name is Chong Li Ting. Metric number AE190094. Today, Sihui and me we're going to present the assignment Bode blocks. The presentation contains 5 parts, which are introduction, Bode blocks, gain margin and phase margin, stability, and lastly is conclusion. Me will present the introduction and Bode blocks, while Sihui will present the gain margin, phase margin, stability, and conclusion. Let's move to introduction. The introduction is about robotic arm, which is an industrial application that we are choosing in this assignment. Robotic arm is metal arm can be used for several manufacturing applications such as welding, material handling, and material removal. In year 2019, Nafisha Ibrahimi from Department of Mechanical Engineering, the University of Texas San Antonio, was proposed a transfer function of dynamic system of robotic arm, which is GS equals to 0.023 over 0.02913 s cubed plus 0.1543 s squared plus 0.1205 s. Next, I will explain the Bode block of the transfer function of dynamic system of robotic arm GS. In order to sketch the Bode block of GX, first we need to change the GX into frequency domain by substituting S equal to J omega. Then step 2, we rewrite the Gj omega with each term normalized to a unity low frequency gain. From the equation, we can conclude that the transfer function of Gj omega contains 2 simple real poles, 1 pole at the origin, and 1 constant. And also, the transfer function have 2 break frequency. One is 0.95207 radian per second, another one is 4.3447 radian per second. In order to sketch the magnitude and phase block using a semi-log paper, we approximate the break frequency into 1 radian per second and 4 radian per second. This is the hand-sketched magnitude block for the transfer function Gx by using a semi-log paper. In order to sketch the magnitude block, we're using the formula to finding the magnitude for the corresponding frequency and break frequency. At the starting point 25.6 decibel, the slope begins downwards and cause an 20 decibel per decade negative slope until 1 radian per second. At the break frequency 1 radian per second has the negative 40 decibel per decade slope. At the break frequency 4 radian per second, the slope continues downwards and cause an 60 decibel per decade negative slope until to infinity. The slide shows the hand-sketched phase block for the transfer function Gx using a semi-log paper. In order to sketch a phase block, we're using the formula to finding the phase angle for the corresponding frequency and break frequency. The phase block starts at negative 90 degree. At the break frequency 0.1 radian per second, the slope begins downwards and cause an 45 degree per decade negative slope. At the break frequency 0.4 radian per second has the negative 90 degree per decade slope. At the frequency 10 radian per second, the slope continues downwards and cause an negative 45 degree per decade slope. At the frequency 40 radian per second, it shows the 0 degree per decade slope. Next, the figure shows the magnitude block by using the MATLAB. First, we can verify our hand-sketched magnitude block is same with the magnitude block in the MATLAB. The same goes to the phase block. We can verify our hand-sketched phase block is same with the phase block in the MATLAB. That's all for my presentation. Now I pass to Sihui to continue the gain margin and phase margin. Thank you.
My name is Sihui, matrix number AE190146. So now I'll continue with phase margin and gain margin. So what's a gain margin and phase margin? Gain margin refers to the amount of gain that can be increased before making the system unstable. The greater the gain margin, the greater the stability of the system. For phase margin, it can refer to the phase shift that can be changed before making the system unstable. Same as gain margin, the greater the phase margin, the greater the stability of the system. Besides, we cannot ignore the importance of gain crossover frequency and phase crossover frequency as well. Gain crossover frequency refers to the frequency at which the magnitude cuts the 0 dB axis in the Bode plot, whereas the phase crossover frequency refers to the frequency at which the phase curve cuts at the negative 180 degrees axis in the Bode plot. So now I'll talk about the stability. For a system to be stable, there will be two conditions, which is the gain margin and the phase margin must be positive, as well as the gain crossover frequency must be lesser than the phase crossover frequency. So here, to start the Bode plot sketching in MATLAB, we'll enter the proposed transfer function inside here, which will lead to the appearance of this equation. Then, by entering the Bode system into the command window, the Bode plot will appear. Next, to look at the gain margin and phase margin based on the sketch Bode plot, we will enter margin system into the command window and they will appear as the title of the Bode plot. To make the MATLAB calculate for the values, we will enter this command into MATLAB and it will help us to calculate it. These four values will be given to us as the calculated values. Here, the results indicate that the gain variation of over 27.7514 dB at phase crossover frequency of 2.0339 radians per second will cause the system to be unstable. Similarly, the phase variation of over 76.4171 degrees at gain crossover frequency of 0.1871 radians per second will cause the system to lose stability as well. Then we can observe the sketch Bode plot created in MATLAB. It can be clearly seen that if we compare it with our hand sketch Bode plot and the Bode plot in MATLAB, it has approximately same shape of response for the transfer function. The gain margin as 28.9 dB and the phase margin as 76.4 degrees are both displayed in the title of the Bode plot. Through the Bode plot, we also can see that the gain crossover frequency is lesser than the phase crossover frequency. Apart from that, as the phase margin is above negative 180 degrees, it is a positive value. For the gain margin, it is located below the 0 dB axis, which also shows that it is also a positive value. Thus, it is a stable system. There are a few ways to stabilize a system in Bode plot if the system is unstable. First, we can change the gain by applying proportional control to shift the crossover frequency. By decreasing the gain constant to the system, it tends to raise the Bode plot vertically upwards without altering the Bode phase plot. This will shift the crossover frequency to the right, which causes the crossover frequency to increase. The system will tend to be stable. In the other hand, Bode plot can also be used to design the controllers to improve the system performances. We can use a lag compensation control to decrease the gain above a certain frequency range. Besides, we also can use a lead compensation control to increase phase at crossover frequency. In conclusion, by using the method of sketching Bode plot, the stability of the proposed transfer function is proved to be stable. Bode plot is one of the simplest methods to plot the magnitude and phase corresponding to frequency curve based on the asymptotic approximation, as it provides sufficient condition for closed loop stability based on the properties of the open loop transfer function. It covers a wide range of frequencies from low frequency to high frequency. Besides, it also provides gain margin and phase margin with the help of the crossover frequencies. By using Bode plot, it is much easier to comment on the stability of the system. That's all from our group. Thank you very much.